Looks like we are starting to have a critical mass of people here, so we can get ready to start whenever we are ready to start the stream. And okay, great. So welcome to the third in my series of lectures, and for today I'm going to start by returning for a short while to a problem we have already seen before, but now we will see it in a completely different context. And we'll consider one more game, but this time it will be the type of a game that has to be analyzed, especially because of the ad hoc type of rules it has. So the previously learned tools will not help us with this one. What does the game look like? So in its easiest version, we have a grid. Possibly initially there can be already some cells that are blocked, and this will again be a two-player game, and the two-player game has the following rules. The first turn of the game is special. The player whose turn it is can pick up a game piece and place it on any free cell on the board. And now the players will be taking alternating turns, and in the easiest version of this game the rule is as follows. So whenever it's your turn, you can take the piece and move it one step up, down, left or right. Once you have performed your move, it's again your opponent's turn. They can do the same. Then is your turn, then is your opponent's turn. And there is one extra rule, and the extra rule is that as soon as a cell has already been visited, it cannot be visited again. So this is what forces the game to be finite. This is what makes it so that you don't move the piece back and forth between two cells forever and have an obvious draw. And the question is the usual: what happens to the strategy? Who wins the game? How do we tell whose winning position it is just by looking at the board in the beginning? And if this is not enough questions, then we can ask more questions. What happens if we play this game, but we don't play it with this particular rules on moving the token, but we place some kind of a chess piece there? So what if it is a chess king? What if it is a rook, queen, or whatever? What if it is a knight? Is it always solvable? Is it always solvable in maybe the same time complexity or with the same algorithm? What happens if we generalize this game completely and I realize that we always, if we define the rules on moving the piece, we always have some underlying graph of the game. So the positions on the board are the vertices of the graph. The game rules specify some directed edges along those you can move. And in particular, does it matter if the edges are directed or undirected? If those are chess pieces or if this is the token, then the edges would be undirected because all of those pieces can move back and forth. Maybe except for a pawn, but for the pawn the game is very, very simple. You start by placing it close to the edge, and then your opponent has no valid move. So yeah, pawn is solvable. But yeah, we can have an underlying graph, and then we can ask the question on general graphs. So suppose I give you a graph, and now we are going to play the game on this graph. The first player chooses a vertex, the second player moves the token to a different vertex, and so on, and you cannot visit the same vertex twice. What can we do with games like this one? And it turns out that the strategy for the game is related to a concept we have already seen on one of the lectures before, and the concept is matching. So imagine a very simple board like this. And let's say we are going to play the game with the chess king. What can we do as the second player on this particular board? We can divide this board into pairs of cells that are adjacent. So we can, for example, do this. This will be 1 and 1, 2 and 2, 3 and 3, and 4 and 4. And for this particular board, we are able to do this perfectly. And what this means is that the second player now has a pretty obvious winning strategy. The first player will start by placing the token somewhere, and the second player will simply move to the second cell in that pair. Now the first player is forced to make a move, and the move will bring the token into another pair, or there is no more moves left. So the first player will move here, and the second player always has a guaranteed move to the second cell in the pair. First player moves here, second player moves there, first player moves here, second player moves there, and now the game is over because the first player has no valid moves left. So we now see how to solve a subset of the cases, not all of them yet, because the existence of perfect matching is not guaranteed. Of course, there can be other grids where there is no perfect matching at all. What happens in those? And the answer is still roughly the same. So instead of just looking for the perfect matching, what we do is we simply find the maximum matching. So let's say we are going back to the original rules. So so if we can only move the token one step up, down, left, or right, we need to divide the cells into as many disjoint pairs as possible. So this is the type of matching when we are trying to cover this board with as many dominoes 2 by 1 as possible. And in this case, we can start doing it greedily. We don't have to apply the full algorithm with augmenting paths just yet. But yeah, now it pays off to start with like the heuristics. So here I can have 2 of them, 2 more. What happens? I'll start greedily, and then I will redraw it just like the algorithm would. So I can have this. Yeah, I lost the cell here, so maybe I was just dumb. Let's be less dumb. Place this one there, here, maybe here, and there, and there is 1 cell left. Yeah, so I was lucky with the choice of my example that I chose one with an odd number of spaces. But of course, on a general board, you don't have to have a matching that will end up like this with just a single cell left unused. It is possible that the total number of free cells is even and there is still no perfect matching. And also for the odd ones, it is also possible that there will be more places here and there that do not fit into the matching. And I already mentioned some augmenting paths, and we know that this is a property that is always true for matchings. And here it doesn't matter whether we are talking about matchings in bipartite graph or matchings in general. If you have a graph, and in the graph you have 2 different matchings of different sizes, what happens? So imagine that this is our graph, and we have 2 different matchings. We will use 2 different colors to mark them. So there's a blue matching that is one collection of disjoint edges, and then there could be a red matching that is a different collection of disjoint edges. 1, 2, maybe 3 like this, 4 like that, 5 like this, and 6 like that. So it can look like something like this. Now, each vertex in the graph is adjacent to at most 1 blue edge, because you cannot have 2 blue edges from the same vertex, and at most 1 red edge. So what this means is that if we look at the entire picture, and let me just for sake of completeness, 1 more blue edge and red edge as well, like this. So it is possible that the matchings do actually coincide in some of the edges, and then it looks like that. It is still true that this vertex has degree 2. There is 1 blue and 1 red outgoing edge, and this same is here. So in this particular picture, the degree of each of the nodes is either 1 or 2. So what this means is that if we are looking at the connected components of this graph, each of them has to be either a path or a cycle. These are the only 2 options we have with degrees only 1 and 2. Furthermore, if it is a path, as we are going along the path, the colors of these edges have to alternate between blue and red, because you cannot have 2 consecutive blue edges. There would be a joint vertex there. And also, as we are going around the cycle has to have an even length. Here it is 2, here it is 4. Because again, as we are going around the cycle, the colors of the edges have to alternate. So, as soon as you have 2 matchings of different sizes, what happens here is that at least in one of those components, you must have more edges from the bigger matching than from the smaller matching. You cannot have equality everywhere or the other matching winning, because when you sum it up, then you wouldn't get the result you are assuming to have. So if there are more red edges than blue edges, you need to have at least one component where there are more red than blue edges. This is called an augmenting path, and many algorithms to construct the maximum matching are based on somehow finding such an augmenting path and then improving the matching. So if you have the blue matching as your current state, and then you find this particular path, that there is a sequence of edges that do not belong, do belong, and do not belong into your matching, and all of those vertices are disjoint from the rest, then you can improve the blue matching by saying that this edge will now be blue, this edge will now be blue, and this edge will be removed from the matching. And now instead of a blue matching with, what was it, 6 edges, now we have one with 7 edges. So we have improved it by 1. So the matchings are one of these like tricky types of problems that is actually polynomial time solvable on all kinds of graphs. But the complexity of finding such paths and doing the actual algorithm differs by quite a lot depending on whether we are in some of the nicer special cases or in the full general situation. In particular, I hope that most people in this room can implement the standard algorithm to do this on bipartite graphs. They're looking for the augmenting path is reasonably easy because as you are going between those two partitions back and forth, you are always going with unused edges in one direction, with used edges in the other direction, and this makes it simple to use just like simple graph traversals. For general graphs, there are polynomial time algorithms like the one by Edmonds, but they are very complicated, and you are building some like contractions of parts of the graph so that you can recompute stuff quickly. Yeah, implementing those is a much bigger pain, especially in a competition setting. But it can be done, and in terms of analyzing of this problem, it is still polynomial time. So we know polynomial time algorithms for general matchings. And from the argument with the augmenting paths, we always know that the maximal matchings in a graph are always all of the same size. Because if you had two matchings of different sizes, then you can use this augmenting path argument to show that the second matching can actually be improved. And so if you have a matching where nothing can be added, then you have to be at the final step always. So all the maximum matchings, the ones with the sorry. What is important now for us when we return back to the game is exactly this argument with the augmenting paths. If the matching we have constructed here is really maximal in the sense that its size is the biggest among all possible matchings, this means that there cannot be any augmenting path. So in particular, if you start at any unmatched cell, and now you start doing a path in any way you like, and the path will be alternating between using a step, an edge that is not in the matching, and using a step that is in the matching. The path eventually has to get stuck without reaching any other unmatched vertex. If we could eventually reach any other such unmatched cell, then it would be an augmenting path, and it would be a contradiction with assuming that the matching was already maximal. So regardless of where we start, and regardless of what path along the graph we take, we will eventually become stuck in this very position that we made a move within the matching, and there is no way to continue. And this is exactly what player 1 needs in our situation. So all of these remaining situations are indeed winning for player 1. And player 1 can win by placing the token into absolutely any unmatched vertex after he has chosen one particular maximum matching, and then the winning strategy is again exactly the same as it was in the previous case. So the second player is forced to move, either already is stuck and we are done, or the second player is forced to move into a matching pair, and then the first player has always guaranteed the possibility to make a next move within the matching. The second player then has to move into another pair. The first player is guaranteed to have a move, and as this is a finite game and the first player is always guaranteed to have a move, then the second player eventually loses. So this is the answer, and this is a very surprising answer because, again, this is one of those cases when the rules of the game have literally nothing to do with matchings. The rules of the game were, here is a graph, start in a vertex, and whenever it's your turn, move the token into a different vertex, and you just cannot visit the same vertex twice. And somehow, inherently, those rules of the game imply that the structure of the graph matters for who is winning the game, and the way in which this matters is the existence of a perfect matching. If a perfect matching exists, then the second player has a winning strategy. If a perfect matching doesn't exist, then the first player has a winning strategy, and the winning strategy is still the same. So find not the perfect one that doesn't exist, but the maximum one, the one with the most edges possible, and then fix one of those matchings in your head and use it as your winning strategy. So this is a very cute example, and I really love the examples like this because they are challenging our intuition. They are helping us build patterns and see the patterns that are maybe not obvious at the first glance. That a very simple set of rules can often define something that is much more complex when we try to analyze it. We can try to analyze how those rules behave. And in general, this is actually a very interesting pattern in computer science, and this is, at least for me, this is the underlying reason about all of those results in computability, like saying that the halting problem is not decidable. It's not the case that this would be just because like the behavior of very complex programs is very hard to analyze algorithmically. It is the case that already very simple sets of rules exhibit very, very complex behavior. And there are very, very small examples of programs about which we currently, even like humans with months spent on analyzing them, are not able to tell what exactly they are doing, how they behave, or describe the behavior of those very small, simple programs. If you have looked at any time into chaos theory, then you would see maybe examples of some such things. I will postpone this for now, but if we have the time during some later lecture, I will actually show you something also on the screen as some more demonstrations of this. So if I have the time, I will get back to this, and I will talk to you a little bit more about like complexity arising from very simple descriptions and this fascinating area that I spent a lot of time on before. But for this particular lecture, I will now retrace my steps a little bit, and I will go back to these domino tilings and general matchings. Matchings, finding matchings turns out to be easy. So easy in the standard theoretical computer scientist way. If I'm not the one who has to be implementing it, then I can call it easy because I'm saying just it's solvable in polynomial time, and everything in polynomial time is easy. So finding a matching is easy, but what about counting matchings? And it turns out that this is one of those funny situations where counting those objects is already much, much more difficult than determining whether or not they exist. And this applies not just to general bipartite graphs, but also to dominoes and to using them to tile planar figures. So in terms of tiling part of a grid with dominoes, if we are asking just whether or not it can be done, this is an easy question to answer. I'm both easy in the sense of I'm a theoretical computer scientist, I don't care. But also in the sense if I had to implement it, it's easy actually to implement it, because what's going on whenever you have a grid, you can use the checkerboard coloring as usual to see that if you have a domino tiling, it must be the case that each of the dominoes is covering one black cell and one white cell of the checkerboard, and therefore the underlying graph we are trying to tile is bipartite. We can view all of the black cells as one partition of the graph, all of the white cells as the other partition of the graph. Now each potential placement of a domino, so the two adjacent empty cells, is giving us one edge in this bipartite graph. And from those edges, we need to select a set that is covering everything or as much as possible and no cell can be covered by two separate dominoes, so we are looking exactly for a matching in a bipartite graph. Finding those is easy, counting those is hard for some reason. When we are in the plane and we are dealing with the dominoes, there are actually specialized algorithms for determining whether or not an area can be tiled. People spend some time on solving these. So this is not like the general case of bipartite matching, for example, for the reason that there is no vertex with degree bigger than 4. This is a special case, so there can be specialized algorithms that solve this faster than by just running the general matching algorithm. And this is indeed the case. There are papers that are solving this in the plane in more efficiently. This is something that, like, big picture idea is generally you can somehow do some kind of a sweeping line processing, and if you have a description of a boundary of an area, for example, then you can much faster decide whether or not it can be perfectly tiled with the dominoes. And for some special cases, like maybe empty rectangular grids and something like that, we have come up with mathematical formulas on the total number of tilings. But doing this in general is much more complicated. And in fact, if we forget about the dominoes for a little while and move to the slightly more general problem of that we have a bipartite graph and we want to count the number of perfect matchings, then it turns out that this problem is not just hard on its own in the sense that we don't know how to solve it, but in this particular area we can again define some kind of completeness and some types of reductions. And it turns out that many other hard counting problems we don't know how to do in polynomial time, and we assume probably cannot be done in polynomial time, can actually be reduced to this particular counting problem. And if you want to look up more about this, this is called sharp P complete. It's slightly difficult to look up on search engines like Google because they don't usually deal well with entries that start with symbols like this one. But yeah, if you plug it into Wikipedia, I will get to the correct site. And probably also Google nowadays will handle this correctly. Or if you write it in words like sharp P, and it will probably get you somewhere close to it. So I will now show you a little bit of about this more. So the main idea is that if you have a bipartite graph, you can do like a small version of the adjacency matrix. So instead of having all vertices on the left side and all vertices on the top, and then have large empty areas, you can just focus on the one quarter that is the important information about the bipartite graph. So you have vertices from one partition here, vertices from the other partition there. If you are hoping to have a perfect matching, then this must be n and n. This must be a square. And the adjacency matrix now contains all of the information here is useful. So for each vertex in the left partition and in each vertex in the right partition, we have a 1 or a 0, depending on whether or not they are connected by an edge. Now, in this type of an adjacency matrix, what does perfect matching look like? So each vertex has to be paired on the left, has to be paired with one on the right, or on the top in this case. So in each row, we have to select exactly one of the cells where there is a 1, not a 0, so the edge has to exist. And also, as soon as we selected this particular one here, there can be no other selected one in the column. So what we get is a collection of ones such that each row and each column has exactly one of them selected. In other words, each such selection can be described by a permutation. So as we go row by row, we are looking at the column indices. So this would be something like 3, 1, 4, 2, and 5. And in order to count all of the matchings, we can mathematically write it down so that we are doing a sum over all permutations. And for each fixed permutation, what we do is we look at the n cells that are determined by the permutation, and we take their product. If all of them are 1s, then we get a 1, and we found the matching. If any of them is a 0, we get a 0, and we didn't find the matching. So we iterate over all possible permutations, and each time we take a product over all I of the adjacency matrix at I and P of I, and what we get is the total number of bipartite matchings. And now comes another one of those places, which is why I'm showing this to you, is that this is something where many people's mathematical intuition breaks. Because what the formula I have written here for the number of bipartite matchings is sometimes called the permanent of a matrix. So this is a matrix, and this formula also for general matrices, not just for 0, 1s, is the permanent of the matrix. And it is very similar to something that is closely related, and this would be put it up here. So if we put one more term here, and the term is -1 to the parity of the permutation P, the new formula is defining some other property of this matrix. The new formula is called the determinant. This has again a lot of practical applications. For instance, one of the very easy ones is telling you whether or not the matrix is regular, and you can also then use it in some algorithms, for example, to solve a system of linear equations connected to these, or talk about its properties. So the determinant is again giving us some useful aggregate information about the matrix, and the determinant is easy to compute. We know how to do this so this very straightforward algorithm would run in cubic time, and this is essentially Gaussian elimination. So we can do operations on this matrix, like adding rows to other rows, and then rearranging the rows, and we can use these operations to set some of the cells to 0, reduce the matrix to a triangular form, and as soon as we have done that, as soon as we have a matrix like this, there is the main diagonal. Everything below the main diagonal is 0. Now, if you take any permutation, it will hit at least one cell in the lower left half, and therefore the product for this permutation will be 0, and the only non-zero permutation is the one when we are going down the main diagonal. So as soon as you get the matrix into this form, you know that the determinant is equal to the product of the entries on the main diagonal, and we are done with the computation. So this is something we know how to do efficiently. But if you erase this term, if you are not counting even permutations with a plus sign and odd permutations with the minus sign, but just summing up over all permutations, it turns out to be the case that we don't know how to compute this efficiently. So the determinant can be computed quickly. The permanent is a mystery. Probably no polynomial time algorithm for that one. So counting matchings is hard, and it is related to deeper and more important results in computer science. But of course, we are smart. We have history with programming competitions, and we know that if you cannot solve it in general, you can still take some special cases of this and set them on programming competitions as tasks. So one of the very easiest questions what we can ask, and a question or a type of an approach that we can usually use for things like this, is let's look at very special cases first. So for example, let's start tiling rectangles only. And if we've spent 15 minutes thinking about counting the domino tilings on general rectangles and still cannot come up with an answer, which isn't surprising because the math behind the result is quite involved, then we will go one more step towards easier problems, and we will say, let's fix one dimension of the rectangle. And this will give us an easy problem we can already solve. So the very easy, very traditional question, and a question many of you have probably already seen more than once. We will start with this very simple case. So we have a rectangle. One of the dimensions is fixed, and for now it is 2. The other one is the only argument, the only parameter we have, and we are asking to count the number of tilings. And yeah, probably no surprises here, but I will go through the motions. What is one nice way to count these? We can ask about the very last column. And in particular, for example, let's look at this particular cell. There are 2 ways in which this cell can be tiled. One of the ways looks like this. And the other way, too many rows. The other way looks like this. if we have chosen this way, we are left with a 2 by n minus 1 rectangle because we have just tiled the last column. If we have chosen this way, then now we can deduce this particular cell has to be paired with that one. This is forced. And now we are left with a rectangle with n minus 2 columns. So if tk is the number of tilings for k columns, we have just derived that for general values of k, we have tk is equal to t k minus 1 plus t k minus 2. We can do this plus because it's obvious that these are two completely disjoint sets of tilings. They already don't match on this particular tile, so no tiling from this particular set can be equal to a tiling from that particular set. So the total size of the set of all possible tilings is the size of the first option plus the size of the second option. Now for the corner cases, we can start directly from 0, and this is the standard bit where some people will struggle with their intuition. What happens for n equals 0 if we don't have anything to tile? The answer isn't 0, the answer is 1. There is one valid tiling, and the valid tiling is the empty tiling. So the instruction place no dominoes is a correct instruction to tile a board of size 0. And for a board of size 1, there is exactly one valid tiling again. Place one domino like this. So you took, when you did this, you took the valid tiling for 0 columns, and you improved it to a valid tiling for 1 column by adding one more domino. Just like you can go from 1 to 2, you can also go from 0 to 1. So that's why it makes also like sense in terms of formulas, not just mathematically, to say that there is one tiling for 0. So we have t0 equals t1 equals 1. And now, yes, everybody knows how to solve this particular recurrence. This particular recurrence is solved by adding one more dash into each of these and saying that, yeah, these are Fibonacci numbers. Okay, so now we have determined the number of tilings for this particular rectangle, and we are happy. Are we happy? Well, we are moderately happy. But yes, this is still a recurrence. This is still something that we need to somehow bash to get the actual numbers out of it. One possibility we could do is we could directly follow what the recurrence is telling us. So we know the values of f0 and f1, so we can now continue on and compute the values of f2, f3, and so on. What's the main issue, and why would we like to use Python to compute those values? The main issue is, of course, that the values start growing pretty quickly. In fact, the Fibonacci numbers grow exponentially, and it is a well-known fact that the nth Fibonacci number is proportional to the golden ratio to the power of n, so 1.618 and something following. And what this means is that regardless of what representation we use for these numbers, so we are using some kind of a fixed base. It can be directly base 10, it can be binary, it can be something like base 10 to the 9 if we are doing some constant level optimizations in the implementation of our begin library. But regardless of what constant base we are using, it means that in order to store the Fibonacci number fn in memory, you will need roughly n cells of memory, roughly n bits of information to store this particular number. And this also means that when you are computing this particular sum, going from fk minus 1 and fk minus 2 to fk, it will take roughly k steps. And therefore, if you want to go from having f0 and f1 all the way through having some specific value fn, it will take you a quadratic amount of steps if you are actually looking into the operations. So if we are just doing counting mathematical operations, then of course directly going from 0 to n and using like very simplified version of dynamic programming, because we are reusing the values we already know to compute the next one. So if we do it like this in a single cycle, it's a linear number of mathematical operations. But as we are going farther and farther, the operations are getting slower and slower, and therefore it is fair to say that the full time complexity will be quadratic in n. And now with more experience among you, I already saying that we probably can do something smarter than this. And one of the things we can do smarter is actually reducing this to matrix multiplication. So what's going on here? So when we know the values f k minus 2 and f k minus 1, the two consecutive values are enough to allow us to compute the next one that will come after that. So when we know these two, we use them to compute fk, and this is simply this one plus this one. And now we can discard the fk minus 2 because we will no longer need it. But in order to continue in the computation, we have to keep fk minus 1. So these are the values we know. And after the step, the values we still have to keep is the value fk minus 1, which will still be needed in the next step, and the new value fk. So this is what we have. This is what we want to have. And the key thing to realize here is that each of these values is simply a linear combination of the values on the left. This one is 0 times this plus 1 times this, and this one is 1 times this plus 1 times that. So we can describe the transformation from going here to there by taking this vector and multiplying by the following matrix. So 0 times this plus 1 times this gives you the first output, and 1 times this plus 1 times that gives you the second output. So this is the specific matrix fancy F for the Fibonacci numbers. And now what this is telling us is that we will start from the initial conditions, 1, 1, and multiply this by the fancy matrix F. We will get 1, 2. If we multiply it by the fancy matrix F again, we will get 2 and 3. If we multiply again, we get 3 and 5. And in general, if we multiply it by the matrix to the power of n minus 1, then from this value, which was f0, and this value, which was f1, we will get the vector fn minus 1 and fn. So this looks smart. Why is this the case? Well, because we can easily show that matrix multiplication is associative. So we can rearrange the order in which we are multiplying. Instead of taking the original vector and multiplying by the matrix once and then twice and then 3 times and so on, we can simply compute first the n minus first power of the matrix and then multiply the vector with this particular power. And we know that raising something to a power is reasonably easy to do, and there is an efficient trick to do it, which is called exponentiation by squaring. If you want to compute a matrix to the power of 2k, you can do this by recursively computing the matrix to the power of k, and then using one additional matrix multiplication by taking this result you already have and multiplying it with itself and thereby squaring it. So in order to get here, you need to get there and then do one additional matrix multiplication. If you want to do a to the power 2k plus 1, you do the same thing and then you multiply it by another copy of a. So this was two additional matrix multiplication to reduce the exponent from 2k plus 1 to k. So we just need logarithmic number of matrix multiplications in order to get the exponent to the value of k. So in this case, we would need logarithm of roughly n matrix multiplications. And now comes the question that will trip up also people who have sometimes seen these results up until this point. Is this a more efficient way of computing Fibonacci numbers? And the answer is that on itself, yeah?
It depends on how
Exactly. That is the precise answer. On its own, it is not. And we are very used from the programming competitions to be doing arithmetics modulo a large prime. Precisely because in the programming competitions generally, the emphasis should not be on like big integer arithmetics if it's not necessary. We are trying to distill the problems to as simple as ones as possible. And if the point of the task is for you to show that you can do the math behind the problem, then it would be just unnecessarily painful to force you to work with the big integers as well and do all kinds of these optimizations. So we are very used to the things like compute the nth Fibonacci number, but do so modulo 10 to the 9 plus 7. And as soon as we are doing calculations modulo 10 to the 9 plus 7, then each of the arithmetic operations here is already running in constant time because we are operating on integers of constant size. And therefore, this would be running in linear time, and this would be actually running in logarithmic time because we are, again, multiplying constant size matrices with constant size numbers. But yes. As soon as we actually want to compute the full value of the nth Fibonacci number using this approach, we have to realize that as we are raising the matrix to a bigger and bigger power, the entries themselves in the matrix will be growing appropriately to the power we currently have. In fact, you can show that if you take the nth power of this particular Fibonacci matrix, all of the entries you will get in the matrix will again be Fibonacci numbers roughly at the index of the power. So when you are doing the very last step of this computation, so you already have f to the power, let's say, n half, and you want to go from there to the f to the power of n, what you have here is a matrix with just 4 entries, but each of those entries is already roughly on the size of the n half Fibonacci numbers. So this is a matrix in which each of those numbers already has a linear number of bits in its representation. And now when you are multiplying this matrix by itself to double the exponent, for each of the cells of the output you are multiplying some constant number of numbers that are linear bits each in its representation. So this is exactly why the claim was correct, that it matters how we do integer multiplication. So if we just use the naive algorithm from primary school, that each bit of this is multiplied with each bit of that, or each digit in any other base, and then we sum it up, then already a single multiplication in this last step will give you a quadratic time complexity, which is precisely what you had if you were doing the 2 nested cycles, and it was much more trivial to implement. So if we are using naive integer multiplication, all of this machinery with the matrices is not helping us a little bit. We will still have the same asymptotic time complexity. But of course, this is a place where we can shave a lot from the time complexity. And as soon as we turn to a faster integer multiplication algorithm, the time complexity will be better. So the final time complexity will be the time to multiply 2 n-bit integers for our algorithm, and then times the log n for the exponentiation of the matrix. So this can actually be a faster way of evaluating the Fibonacci numbers. But we need to be smarter about all steps of the implementation, and just blindly using the exponentiation by squaring is not enough to do that. And now for a bit of higher math, as we are here. This particular matrix cannot just give us a discrete formula like this that we can use to compute exactly the values of Fibonacci numbers more efficiently. It can also tell us a lot about how quickly the Fibonacci numbers grow. And you have probably, many of you will have seen a formula for Fibonacci numbers that looks something like this, that the nth Fibonacci number is actually exactly equal to the following monstrosity: 1 over square root of 5 times 1 plus square root of 5 over 2 to the power of n minus 1 over square root of 5 times 1 minus square root of 5 over 2 to the power of 10. I hope I got the signs right, but if not, it is something very, very similar to this. I think I get them correctly. So what's this? How does this appear from nowhere? And how is it related to this particular matrix? Before I answer that question, I will make one more observation. The observation is that this particular term is in absolute value smaller than 1. As we are raising it to the nth power, it will very quickly become smaller than 1/2, and eventually it converges towards 0. So Fn is actually actually be obtained by rounding this to the nearest integer, and this should be true already from n equals 2 or something like that. So this is the only term that matters, and this is why the Fibonacci numbers are then proportional in size to the golden ratio, which is exactly this constant raised to the power of n. Okay, so where did this come from? How is it related to this particular matrix? Some matrices so each matrix is an operation of vectors. You put a vector in, and you get a different vector out. So this is usually called a linear map or something along those lines. And multiplying a vector by the matrix somehow usually influences the length of the vector. And if you look at some very special matrices, like for example, we can have a transformation in 3 dimensions, and the matrix can look as follows: 3, 2, and 7, and everything else is 0. So there are only numbers on the diagonal and nothing else. So what this matrix is doing to any input vector is that the first coordinate gets multiplied by 3. So when you have the vector multiplied by this matrix, you will have 3, 0, 0, multiplying the first to give you the first output, 0, 2, 0 to get the second output, 0, 0, 7 to get the third one. So if you plug in x, y, and z, you will get 3x, 2y, and 7z. So a simple matrix like this one is essentially just doing scaling, and it scales by the factor of 3 in one of those dimensions, by a factor of 2 in another dimension, by a factor of 7 in the third dimension. And now already we can start asking the question like this. So suppose you have some unknown vector u, and you multiply the vector u by the matrix M, so it gets scaled, and then you multiply it by the matrix M again, and again, and so on. What happens in general? So you have the vector u, you multiply it by the matrix M to the power of n, and you will get some new vector v. What can you tell about the size of the vector v in terms of the... So we are interested in the size of the output vector and how it relates to the size of the input vector. What's the relationship between them? What can you tell me about those?
You multiply by a constant on the left, you also get multiplied by a constant on the right.
Can you give me an upper bound if I tell you that the input vector has length exactly 10? Can you give me an upper bound of the length of the output vector? Yeah, we are doing this specific matrix M, so 3 to 7, this one.
No 7 times.
Yes. So the length of V must be less than or equal than this 7 to the power of n times the size of U. Yes? So what's going on here? So whatever vector comes in, it gets scaled 3 times in one coordinate, twice in the other coordinate, 7 times in this particular coordinate. So if we have, it would be nicer to draw it in 2D, but it's too late for that. So anyways, but if you now look at the size of the new vector, what is the size of the new vector? The size of the new vector is the square root of 3x squared plus 2y squared plus 7z squared. This is obviously less than or equal to the square root of 7x squared plus 7y squared plus 7z squared, and that would be I got a factor of 3. Yeah, I got a factor of 3. I don't want that. Yeah. I probably have to draw the picture anyways. So let's draw a picture in 2 dimensions. So you had an original vector, and now you produce the new vector by scaling it twice in this direction and 3 times in the other direction. Imagine
You just
Yeah.
factor out the 7.
Yeah, you were right.
You pull it out.
Yeah. I got confused, but yes, if you factor out the 7 from the formula, you get actually what I was trying to show. Okay, thank you very much for the correction. So anyways, the point is here that if you have a vector that is directly pointing upwards and you are scaling by 3 times in this direction and twice in that direction, you will get a scaling by the full factor of 3. If you had a vector that is pointing directly in the other direction, this will get scaled by a factor of 2, and anything in between, you are going from the factor 2 to the factor 3 gradually, and you can do this by doing the orthogonal projection on the original and showing that as you, or the orthogonal projection of this. So if this is your input vector, these are the parts of your input vector in the directions of the coordinate axis, and the final image can be produced by taking this projection and scaling it by the factor of 2, taking this projection and scaling it by the factor of 3, and then adding those together, and you will get the final scaled vector. And this is exactly what is going on also in the general case. If we have any general vector x, y, z, we will take the projection onto the x-axis and scale it by 3, the projection onto the y-axis, scale it by 2, projection onto the z-axis, scale it by 7, add it all together. The best we can get is if we have a vector directly pointing in the direction of z-axis, and that one will get scaled by the factor of 7, and all other vectors will get scaled slightly less. But in fact, you can now realize the following, and let's look at this one more time in 2D, and I will do it more precisely. So what we have now is a general vector u, and we are going to scale this vector u by multiplying it n times in a row with the same matrix, and the matrix will now be this 2, 3, 0, 0. So everything that is pointing in the x-axis direction will get multiplied by 2, and everything that is pointing in the y-axis direction will get multiplied by 3. So if the starting vector is a special case of a vector pointing directly along the x-axis, it will get doubled in every step. Each time you multiply with the matrix, it will get doubled. But for any other vector, so if it's in a general position or if it's pointing directly upwards, there is always a non-empty projections on the y-axis, and the final result will be such that this particular vector is then multiplied by 3 to the n, the other part will be multiplied by 2 to the n, and the resulting size of the resulting vector will be the combination of those two. So it will be strictly greater than just this particular, the size of this particular projection, times 3 to the n. And if the original vector is a constant, this is also a constant, and we are now taking this constant, slightly smaller than the original vector, but still a constant, and multiplying by the power of 3 to the n. So in this particular case, if we start from any general vector that has at least a slight fraction of it going in the direction of the z-axis, which is where the matrix is scaling by the biggest factor, we will always get not just this inequality, but we will get that the size of the resulting vector is actually asymptotically proportional to 7 to the n times start of the size of the initial vector. So whenever you have a matrix that is scaling in each direction, then for almost all of the starting vectors, you will get a growth that is proportional to the biggest of those numbers. You need to be in a very specific subspace of vectors. You need to be exactly orthogonal to this particular direction, and only then you will get a slower rate of growth. And this is something that is very useful when we have linear recurrences like the Fibonacci one, when we represent them by matrices like this one, because exactly what is going on here is that we have a vector, and when we are trying to find out the nth value of the Fibonacci numbers, we are multiplying the vector by a matrix raised to the power of n. And if this were a matrix that was scaling the vector, it would be scaling the vector by the same factor in each iteration, and the rate at which it scales the vector would then correspond exactly to the rate of growth of those Fibonacci numbers. And it turns out that this is actually always the case, or at least except for maybe some degenerate cases like a matrix of all zeros and so on. So if you have a nice regular matrices, this is always the case. And why is this so? Well, because it is not just true that this particular very specially constructed matrix is a matrix that scales. Yeah, right, because you can represent all kinds of things with matrices. You can also represent, like in 2D, if you have 2 by 2 matrices, you can also already represent, for example, rotation in the plane with matrices. So if you have a matrix that looks like this, there is a cosine of an angle, a sine of an angle, again a sine of an angle, and a minus cosine of an angle. Then if you take any vector x and y, multiply it by this matrix, what you will get as a coordinates of a new point that is rotated by, so this was xy, and this will rotated by an angle of alpha will be the output you get. The size of the new vector is the same as the old vector. There is no scaling going on. There is just a rotation going on, right? Wrong. Well, because this is what the matrix does as long as the inputs for the matrix are just vectors with real values. But if you take the exact same matrix, so this is a matrix containing just real values, and say that the possible inputs are all possible vectors of complex numbers, it turns out to be the case that there are always these canonical directions that correspond to what was going on here with the x, y, and z axes. So you can always, in the complex space, find these directions, that if you look at this particular direction, the matrix, the only thing that it does is scales by some particular factor. And these are the magic words you may have heard somewhere. They are called eigenvalues and eigenvectors. So these are properties of this particular matrix. Each matrix has its own set of these eigenvectors. These are those complex directions, and sometimes real, sometimes not, in which the matrix is doing the scaling. And the eigenvectors, each of them comes with an associated eigenvalue, which is, again, a number, generally a complex number, that is telling you the factor by which it scales in that particular direction. And this then is very, very useful both in general, because what is this formula? This formula is telling you that there are like 2 directions in which the Fibonacci matrix scales, and the size of the new vector essentially then corresponds to this. So this is the factor by which it scales in one of those directions, and each time you multiply it by the matrix, it gets the fraction of the vector gets scaled by this, and this is the factor by which it scales in the other direction. This particular is less than 1, so the size of the vector of this particular part of the vector will get smaller and smaller in every iteration. So this is the general idea behind that. And yeah, so the easiest way how we can use this when we are doing combinatories and when we are analyzing recurrences, and we want to go from, okay, I have the recurrence, I can represent it as a matrix, and now I would like to know how quickly does the number of these objects grow. So what is the asymptotic growth rate of Fibonacci numbers or whatever else I can describe by such a recurrence? And the answer is, you take the matrix, you plug it into Wolfram Alpha or other computational engine, or you can actually, so this is something you can actually also implement on your own. There is the thing called characteristic polynomial, where what you do is you subtract x on the diagonal, and then you formally do the determinant of the matrix, and the eigenvalues can be shown to be exactly the roots, the complex roots of this particular polynomial of the degree that is the size of the matrix. So it can be computed, but yeah, in practice, when I was doing similar things during research, and yeah, I'm not going to implement this myself, so I just take the matrix, I plug it into Wolfram Alpha, and ask it what is the biggest eigenvalue. And it tells me. So if you plug this matrix in, the eigenvalues are obviously 3, 2, and 7. The eigenvectors are the directions x, y, and z axes. and the biggest eigenvalue in absolute value or in terms of complex numbers in its like modulus or whatever it is, size of the value is in this case 7. And if the biggest eigenvalue has size 7, it's telling you that whatever vector you plug in, when you multiply it by this matrix, you will get a vector that is at most 7 times that big. And in fact, almost all vectors will have this property that whatever you plug in, the output is roughly 7 times that big. And when if you repeat it, the size of the output will grow with exactly the factor of 7. Because if the starting vector is like chosen independently from the matrix, so it is some random sequence of values, it is almost certainly not perpendicular to the direction that corresponds to the biggest eigenvalue. So for almost all starting conditions, for example, for the Fibonacci sequence, if you change the initial 1, 1 to 2, 7, or 3, 15, or whatever you like, 5 and minus 2, you will almost always get the rate of growth that will be proportional to the golden ratio, simply because you need to hit the very specific starting conditions where this vector is orthogonal to one particular direction in the vector space in order to get slower rate of growth. So it is possible, but it is very, very unlikely. And so in general, so what you can always do is, if you know the biggest eigenvalue of this particular matrix, you have a guaranteed upper bound on the rate of growth of the number of those objects, or the size of the term of the recurrence. And in general, you can expect that this will not just be an upper bound, but this will be the exact asymptotic estimate. So the biggest eigenvalue of this particular matrix is exactly the golden ratio. And for almost all starting conditions, this is the exact asymptotic rate of growth of the sequence you will get. Okay, we still have some time before the coffee break, so let me show some more complicated examples where you can apply thinking like this. Like, probably the biggest point of this part of today's lecture now wants to be the following, that this transition from having a recurrence to using a matrix to speed up the calculation of the nth value, in particular if we are doing it modulo a small prime or something like that, so that we can do the arithmetic quickly, is not something that is just inherent to sequences like Fibonacci, but it is also applicable to all kinds of dynamic programming. Why is this the case? So let's look at some more complicated versions of tiling. So for example, let's see what happens if we have rectangles of the dimensions 5 by n. What we can do now is we can imagine that we will start by trying out all possibilities for tiling the last column. Right. This is one of those possibilities. There are finitely many. We can iterate over all of them. What they will produce is in the previous column. So we have, if this is, for example, one of the options we are currently examining, we see that we now didn't get exactly the same problem as before. The problem is that we have one fewer columns because we have filled the last column completely. But in this column, we actually have some noise. There is already one cell blocked here. But that doesn't matter. We can still apply the same next step. So we take the next column, and everything that is currently empty in that column, we'll try all possibilities to tile it. So for this one column, we can choose one possibility that looks, for example, like this. And now we get to the next column. And again, some of the cells are already blocked. Some of the cells are still available. And we are asking again the same question. Go over all possible ways of tiling it and try all of them. If we just implemented this recursively, we would get an algorithm that is actually generating all possible tilings one at a time. by backtracking. So when we get to the end, we either successfully complete the entire rectangle or not, and then we go one step back, try a different tiling, and so on. So this would be exponential in time complexity, but we know that we can now apply memoization, because if later on I try a different combination here, but then I get the same question, that I still have n-2 columns, and exactly the second and the fifth one are blocked. If this is a question I have asked before, the answer hasn't changed since. The number of valid values to finish this tiling is still the same as it was 5 minutes ago. So what I can do is, whenever I learn the answer to such a question, I can store it in memory, I can use memorization, and then I can reuse it whenever it appears one more time. So what I get is a finite number of states. The description of a state is the number of columns we still have left to process. So there are n options for, or the order of n plus 1 may be options for the number of columns. And then we need to store the pattern, which rows are available, which rows are already blocked. So this is 2 to the number of rows, or 2 to the 5 if this is a constant. So this is the number of states, and from each state we have some transitions. So for each state we will try all possibilities of tiling the column, and this will bring us to the previous states. So we can think about this recursively in terms of memoizing these values. We can think about this also in terms of like iterative dynamic programming. When you start with just a single column, you try all possibilities for that. Most of them will fail, so we'll return a 0. And if this is an even number, then you will have exactly one combination when you tile the entire column and get a valid tiling. Then you will do it also for the combination where something is blocked, and some of those will actually solve. And once you know all of the values for one column, you can move to the second, you can move to the third, and so on. So far so good. And we would get some kind of a time complexity that is exponential in the number of rows and linear in the number of columns. Yeah? Do you see how to do such a solution, right? And now the key observation is this. Suppose you have already computed all of the possible values for this number of columns. So for each combination of these cells being blocked or available, you have already solved the problem. And now you are looking at the dynamic programming. You are incrementing the variable in the outer cycle, and now you are going to process all of these combinations. What happens for each of them? So whenever you have a specific combination of cells in this column, you will be trying all possible tilings, and each time you tile this particular column, you will then look up the previously computed value for the previous column and add it to your particular answer. So you are iterating over some options, and for each of those options you find, you add some of the previously computed value to your answer for this particular pattern. So what this means is, if you see the DP table for this column as a vector of length 2 to the number of rows, so these are the values you have previously computed and stored in memory, and now you are going to compute the new vector of those values for the next column. This particular cell will be the sum of maybe this cell twice, this cell, and this cell, because like different combinations of tiles here can generally, I don't know whether it does, but in general when you are doing DP like this, it's possible that you are trying different options, and different options may lead to the same previous state. So if that happens, then you will be adding this particular previous solution to this one with not just once, but with a factor of 2 or 3 or 4. And what we can observe now is that each value in the new vector is simply a linear combination of values in the previous vector, because we are just adding them up. And moreover, this logic is not particular to this specific column. When we will do the next computation and the next computation, the logic will always be the same. The next cell of the next table at this coordinate will be computing from these cells in exactly the same manner. Those one twice, this one once, this one once. So this is the main big picture observation, that going from the state for x columns to the state for x plus 1 columns, this is a linear transformation. This is a vector of size 2 to the r being multiplied by a matrix to obtain the new vector. And the matrix will be the same for the next row and the next row and so on. So one thing you can do is you can get rid of the linear factor in the number of columns and change it to a logarithmic factor, because we can now use matrix multiplication if we know the values for in the initial vector after processing one column, and we want to know the vectors at the very end of the matrix. We just need to take the initial vector and multiply it by this particular matrix taken to the power of n minus 1, and we will get the answer. And moreover, if you are not doing this at the programming competition, but you are doing this in terms of like combinatorial research, and you are interested in a number of such structures, you can get a very quick and dirty answer exactly by knowing about eigenvalues, eigenvectors, and how they behave, because you can take this matrix. So you can actually, when you have implemented the DP, you can actually extract the matrix directly from the DP. So you just run this iteration, and you will, instead of adding this value to this cell, you will make a note in the two-dimensional matrix that from here to there, I increment the cell by 1. So the cell at coordinates this and this will be incremented by 1 in the matrix whenever you are doing this step of the computation. So this is a matrix you can very easily extract from your dynamic programming program, and then you plug it into the Wolfram Alpha, and it will tell you that the rate of growth is this. So the asymptotically, the number of tilings of 5 by n rectangle for n even is some constant to the power of n. And the specific constant will be related to the value of this eigenvalue. Yeah, and counting these matrices is definitely not the only application of this, but many different things, many different flavors of DP can be thought of as applications of this. So the transformation you are doing is in many contexts a linear transformation, and you can always then do this next step conceptually. So another example is suppose you are given some alphabet. For example, you have letters A, B, C, and D, and you have some forbidden substring, one or even multiple, like maybe you are said that no substring Baba can appear in your string. And now we have the set of all strings of length n, and we can divide it into two groups. One of them are the strings that are good, that do not contain any copy of the substring. The other are strings that are bad, that contain at least one copy of the bad, or of the forbidden substring. Asymptotically, which of these two piles is bigger? Which one?
Good one. The one that doesn't contain Baba.
The one that doesn't contain Baba. I think that there's more of them. Do the rest of you agree, disagree, still think about it? Like the obvious thing is if we have strings of length n, and this particular alphabet, there are exactly 4 to the n strings of length n, because we have 4 options for each character. And even if you divide it exactly into halves, then each would have 4 to the n divided by 2 strings. And the bigger of the two piles will still asymptotically have 4 to the n strings. So this is something that has to happen. One of those two piles asymptotically has to have the size 4 to the n. Maybe both, but is this the case? And which one is the bigger? Do we have any more opinions? Why?
Because, like, my intuition says that if you have a sufficiently long string,
Yes.
the probability that you do have Baba as a substring grows and gets very close to 1.
Yeah, that is a very good intuition. It's much more visible if you do some things like forbidden digit only, so a single character. So let's think about decimals. What happens if we divide decimals between good ones that do not contain any digit 7 and bad ones that do contain some digit 7? If you start with very small examples, then like in the tens, you will still have like there's everything that starts with a 7 and everything that ends with a 7. So quite a lot of them are bad, but and the rest is good. But as you are progressing, what happens? So here's the one of way of like getting the right intuition is exactly as you said, that if you imagine a very big number and you generate it at random, so each digit is randomly chosen, it is almost certain that there will be a 7 somewhere
the probability of getting no 7s is very, very low. So almost all of the big numbers will have at least one 7. This will be the bigger set. Another way of looking at it is actually doing the counting. So after you fix the first digit, to get rid of technical cases with leading zeros, if you want to produce a number with n digits, and none of them are allowed to be a 7, you only have 9 options for each of the remaining digits. So there are roughly only 9 to the power of n digit numbers that do not contain a 7, and all of the numbers are 10 to the power of n minus 9 to the power of n are the remaining ones. So as n is growing bigger and bigger, this one number is getting much, much smaller than this one, and almost all of the numbers fall into this category. So the number of the bad ones that contain some digit 7 is growing with the ratio of 10. So asymptotically there's 10 to the n of them, and there's only 9 to the n of those that do not contain any 7s. And the same will be here. If you have a longer forbidden substring, again, if you imagine very, very long strings randomly generated from this alphabet, almost certainly the substring will appear somewhere, because like for any 4 consecutive letters you have probability 1 over 4 to the power of 4 that this is where it will appear. And if you have like many, many independent tries within the string, sometimes it almost certainly happens. And how can we actually get the exact asymptotic estimate for the number of such strings? Well, we can start by, again, doing dynamic programming. So imagine the very standard programming competition task. Given n, count all strings over this alphabet of length n that do not contain the substring baba. How can we do this? We can imagine a finite automaton that is looking for the string baba. We have an initial state when we haven't seen anything useful. When we have seen the character b, we move to the state that we already have 1 letter of the string. When we see the character a afterwards, we move to the state when we have seen already 2 characters of baba. Anything else, any other character will have a different effect. So if we see another b after the first b, we are staying here. If we see anything else, we are returning to the start. And we can continue like this. And this is already an accepting state. And whatever comes next, we have already found the substring baba in the string. So in order to, you don't have to think about this and determine all of these edges manually. You can if you want to, but you can also let your program do this. So we are just saying that the state we are currently in is the longest prefix of baba that we currently have. And from this state, we try all possibilities. What is the next letter? And for each letter, we can recompute what is currently the longest prefix. If it is length 4, we have already found the substring. And if now, if at any other moment, if at this moment we get a C, we go straight to the beginning. If we get another B, we go there. And we can ask our program to recompute this very quickly. And now, as we have this automaton, we can already do the counting. So what we are going to do is a very simple dynamic programming. For each length of the string and each state of the automaton, we will be calculating the number of ways in which we can reach this particular state. At the very beginning, if we have just if n is 0 and we have just the empty string, we have 1 way of being here and 0 ways of being anywhere else. And if we know these values for the previous length, and now we are going to append a new letter. So if we have 17 ways of reaching this particular state, now we have 17 ways of being here and then processing the letter A and going there. We have 17 ways of being here and processing the letter B and going there. So the new count for this state will be incremented by the old count for that state. Then the new count from this state will be incremented and so on. And this gives us dynamic programming that is able to compute this for any value of n. And now we can do the new conceptual step we just learned, that if you have the old 5 values and you compute them, you could compute the new 5 values from them by doing this iteration of over all possibilities for the next letter. You are doing, again, a linear transformation. Each of the new values is a linear combination of the previous values, so you can represent it by the matrix, and then you can ask about the biggest eigenvalue of the matrix to get the asymptotic rate of growth. If you feel like a hacker, you don't have to even bring up Wolfram alpha. What you can do is that you can realize that if you have the answer, so if you already have the DP, you can get a very quick and dirty estimate even without the eigenvalues, because you can use the DP to compute the number of such words for 17, 18, 19 characters, and then when you take the count for 19 and divide it by the count of 18, you will not get the exact value of the constant, but you will get something that is pretty close. And as you are computing bigger and bigger values, the ratio of the two following terms will be converging to the actual exact answer. So you can compute the exact answer as the eigenvalue of the matrix, but you can also estimate its value very reasonably by just running the DP until it fits still in your time and memory, and then computing the ratio of the last two values you were able to compute. Of course, this was the fancy way of doing this problem. The lazier way of doing this problem is to have more states. So instead of having this fancy finite automaton, you can simply say that your state are the last three letters of the string, and the only forbidden transition is if the last three letters of your string were BAB, you are not allowed to append A, and that's it. So in this case, you wouldn't have 5 states, and you wouldn't have a 5 by 5 matrix. You would have 8 states, or is this, no, sorry, there is 4 options for each of the letters, so 4 times 4, 16, times 4, 64. So instead of a 5 by 5 matrix, you would get a 64 by 64 byte matrix from the lazier DP, but it would still have the same biggest eigenvalue, because it is still ultimately computing the same thing. So even if you do lazier DP, you are only punished by having a bigger matrix. So this would then also, if you were still be trying to compute the answers exactly for large n and modulo a prime. So if you were asked determine the number of such strings of length 10 to the 18, but it is enough if you determine the remainder modulo 10 to the 9 plus 7, then you could simply do the matrix multiplication. But if you start with a smart DP that only has 5 states, you will be raising the 5 by 5 matrix to the power of n. If you start from the dump DP that has 64 possible states, then you would be raising a 64 by 64 matrix. And this can then have a very different constant in your time complexity. So I have encountered competition problems before where part of the optimizations you had to do was actually do the thinking bit when designing the DP in the first step, so that your matrix that you are then raising to the nth power would be small enough to fit into the time complexity. And yes, we are past 10 o'clock, so we should have a coffee break. So let's move on. We'll still be playing around with matrices for a little while longer, and now I want to show you that matrices can do a lot more than you would maybe expect at the first glance. So far what we were doing was we had a linear recurrence of some type, or maybe a linear relationship between a set of old values and a set of new values after one more step. And when we have any type of recurrences like this, they are looking one step into the past, then and the calculations that are linear combinations, we can transform them into matrix operations. But it turns out to be the case that with matrices you can do even crazier stuff, and you can generate sequences that are much more involved. So for example, suppose you have a sequence that looks like this: 1, 1, 2, 2, 4, 4, 8, 8, and so on. Can you generate such a sequence using matrix and compute the nth element quickly using matrix multiplication? Then, well, this is like we are alternately multiplying by 1 and by 2. How can we do this? Well, we need a state of size 2. And so you have x and y. From the x and y, you will go to y and 2x. And from the y and 2x, you will go to the 2x and 2y. And if you keep looking at the first element of this sequence, what happened is after 2 steps it doubled. So if you start from 1, 1, and you can do this, you will go to 1, 2, and 2, 2, and 2, 4, and 4, 4. So by swapping between those two places, and when you are going from here to there, you multiply by 2, but when you are bringing it back to the front, you are multiplying just by 1. Then you can do it, and this is in fact the linear transformation. You are taking this element there, this also happens here, this element goes there, and this element is doubled and goes there. So you are just doing multiplication by the following matrix. So 0 and 1, 0 times this plus 1 times this gives you the first output, and 2, 0 gives you the other output. You can also interleave 2 separate sequences like this. So in general, we can generate very many sequences in a way that we will have a vector. The first value of the vector will be the thing we actually want to generate, and as we are going through the steps and multiplying it again and again by the very same matrix, at the first position in the vector will be the sequence we are trying to generate. So in order to generate the nth element of the sequence, you take the starting vector, multiply it by the matrix to the power of n, and then you get the element at the index n. We can say that this is index 0 so that we don't have those pesky -1s. So you can take multiple sequences and interleave them also between each other. So you can have a sequence like 2 to the 0, then 3 to the 0, then 2 to the 1, then 3 to the 1, and so on. How would you do this? Yeah, well, you can combine 2 such sequences. So you can have a vector that looks like this. So there will be something, and 2 to the x, and the 0, and the 0, and the 3 to the x. And now you will switch those two. You will switch those two in every step. And then, so this is to do one of the delays, this is to do the other delay. When you are going there, you can multiply. So here we will get, this one will be doing times 2. So here we will get 2 to x plus 1 and 0, and this one can also be doing times 3. So we'll get a 0 and 3 to the x. And when you do one more step of such multiplication, then this will become 3 to the x plus 1, 0, 0, and 2 to the x plus 1. And this first element of the sequence, so if you have already these 4 elements in your vector, and each matrix multiplication is doing this step and this step and this step, then in order to produce the corresponding output in this part of the vector, you just need to take the appropriate linear combination. So you can say that this is always this cell plus this cell will also be stored here, and this will give you 2 to the x here, 3 to the x there, 2 to the x plus y1 here, and also in the next step. So you can interleave 2 sequences very easily. And what's even more surprising is that the sequences don't actually have to grow exponentially. What about the sequence 1, 2, 3, 4, and so on? Just the normal national numbers. Can this be the outcome of suitable matrix multiplication? And the answer is yes, without any issues. So suppose, so the trick is that if you have a vector with some value x and also a constant 1, so we add another element into a vector and the element will be a constant 1, you can transform it to x plus 1 and again a 1. And this is again a linear transformation. This x plus 1 is the sum of this and this. And the 1 is 0 times this plus 1 times this. So the matrix is again almost the same as the for Fibonacci. The first output is the sum of the inputs, and the second output is just the second input. So if you add a constant into your vector, this times this equals this. So repeated multiplication by this matrix for this specific initial conditions. This is kind of abuse. So this is kind of going contrary to what we had previously. This is abusing the initial conditions in such a way that we are doing something very special with the matrix, but it works. And you don't need to just so when you have a variable, when you have an element of the vector that is doing a linear sequence, you can also then do the quadratic sequence. So if you have a sequence 1, 4, 9, 16, 25, 36, and so on, you can also produce this using matrix multiplication. What will you do? You will have a vector of form x squared, x and 1, and you want to produce a new vector that is x plus 1 squared, x plus 1 and 1. And again, you can do this. So this is, again, just the linear combination. So this is x squared plus 2x plus 1. In other words, the first element of the output is once this, plus twice this, plus once this. So if you take this vector and multiply it by the matrix 1 to 1 in the first column, now x plus 1 is this plus this, so this is 0, 1, 1, and 1 is just this, 0, 0, 1. This vector multiplied by this particular matrix of constants gives you that vector. So we start it from 0, 0, 1, which are the initial conditions. So this is 0 squared, 0, and the 1. Multiplied by this matrix to the power of n, you will get n squared and 1 in the vector. So you can do polynomials. You can do all kinds of things. And even if you have recurrencies that are looking not just at a constant number of steps into the past, but somewhere farther, it still may be possible in some cases to reduce them to matrix form. So for example, suppose you have a recurrence of the form that x0 is 3 and for all n greater than 0, xn is twice the sum of the previous values, x0 plus all the way through x min minus 1, and then let's say plus 3. If you have a recurrence like this, and the very helpful feature that can help you go from here to suitable version of matrix multiplication is always you can ask the question, how would I implement this using only a constant number of variables per iteration? So we want to do the very standard iterative version of evaluating such a recurrence. And what we want to do is we want simply to evaluate every step in constant time, and we want to do it one step at a time. So what you could do here when you are trying to generate this sequence, you would keep variables like the current value of 2 to the x, the current value of 3 to the x, and a Boolean flag or something along those lines. And you can always take these old variables and then somehow modify them into the new ones. So if you were to compute this sum in a not quadratic but a linear time complexity, what you can do is you can store the prefix sum of your sequence so far in a variable. And in order to, instead of recomputing it from scratch, you can just reuse the previous value. So what you will be doing in your program is you have the sum of the previous values. This is initialized to 0, and the current value, this is initialized to 3. And when you have these two values, then you can compute the new value. The new value is twice the sum of all previous values and also the next term that just appeared, and plus 3. And the new sum of the new prefix sum is then the old prefix sum plus the term we just processed. So something like this. And then this becomes the new P, this becomes the new C. So the next element becomes the current element, the new prefix sum becomes the old prefix sum, and we are iterating it over and over again. So the initial conditions, when we initialize the variables, this will be simply the vector you start from. And the transformation, where you go from these to those, will be is a linear transformation that can be described by a matrix. We see that here we have the constant plus 3, so we also have to include the constant 1 into the initial vector so that we can do the plus 3. So we would do something like that. The initial vector would be the 0, the 3, or we can have the sequence itself should be at the very first term. So 3 is the actual term of the sequence. 0 is the sum of the terms previously. And the 1 is a constant. And now we are going to multiply it by a suitable matrix. And we see that twice this plus twice that plus 3 times the constant will give you the new value. And the new sum will be the old sum plus these values, so 1, 1, and 0. And the 3 will, so the 1 will remain the 1, so this will be 0, 0, 1 as well. So this is the conceptual step you can make in between. And once you know how to do this, then you can play around with all kinds of other recurrencies. So for example, if this was a sum, not with just pluses, but with alternating pluses and minuses, you should still be able to adapt it into such a form. So as an intermediate step, ask the question, how would I recompute the new value from the old ones in constant time? And if you can find a trick to do this, then usually all of the calculations you are doing are still linear combinations of all values to get the new ones. And as soon as that happens, you can represent it by a suitable matrix. And this will then allow you to speed up the calculation. So if you want the nth term from the initial conditions, and if you want it modulo a prime so that we don't care about the complexity of arithmetic operations, you can do it in logarithmic time by taking the initial conditions, multiplying by the matrix to the power of n, and getting the output. So these are probably this is, from my point of view, the most useful and least commonly known trick, that you can actually use matrix multiplication also to solve recurrencies where there are not only references to previous terms but also to polynomials. So tricks like this would be usable, for example, to solve something like x0 is 4, x1 is 7, and xn plus 2 is 3 times xn plus 1 plus xn plus n squared. If you have a recurrence like this, what you will be doing when you want to represent this using matrices is that your current state are the 2 consecutive values of your sequence, and then the values 1, n, and n squared, so that you can do the polynomial factors. And then once you know these 5 values, you can recompute the values shifted by 1. So instead of n squared, n plus 1 squared, and instead of terms of with indices n and n plus 1, terms with indices n plus 1 and n plus 2. So again, one step of calculating such a recurrence can be converted to a matrix operation on a vector of size probably 5 in this case, and this allows you then to speed up the calculation to logarithmic time from linear time, even if there are extra polynomial terms in the recurrence. Okay, so this was the excursion in the world of matrices, and as we had recently had a request on talking about convolutions, I will now spend a bit of time showing you a few of my favorite examples of what you can do with convolutions. And yeah, I will start by explaining what it is and very quickly how it can be used, and then I will show you a few nice trick examples for them. So one thing we have already mentioned here today when we were trying to calculate the exact values of Fibonacci numbers efficiently is that if we want to use the trick of exponentiation by repeated squaring and use this to compute them more efficiently than the naive way of doing it in a cycle, we need faster integer multiplication. So what's going on there? So we have 2 integers. Each of them is a sequence of digits. And the naive way in which we can multiply those two integers, if they have each roughly n digits, involves n squared elementary mathematical operations, because we have been taught to do it like this, that you take this digit and multiply this number and write it down, and you take this digit, multiply this number, write it down and sum it up. So essentially each digit gets multiplied with each other digit and we get the result. This is correct, but this is also slow. And there have been some approaches, some people thinking about better solutions for this problem. And an intermediate step that is reasonably easy, both conceptually and in terms of implementation, is the idea by Karatsuba, which is that if you have two big numbers like this, a number A, a number B, you can split them into halves. So this number A can be seen like the first half, A1, times 10 to the power of n half, plus the second half, A0, and this can be seen similarly as B1 times some power of 10 and plus B0. And now what we want to evaluate when we want to compute A times B is A times B equals A1 plus, times 10 to some k plus A0, and also this is times B1 times 10 to the k plus B0, and we can rewrite this as this is A1 times B1 times 10 to the 2k plus A0 B1 plus A1 B0 times 10 to the k and plus A0 times B0. So what this is telling us when we write it like that is that in order to multiply two n-digit numbers, I have now reduced it to 4 multiplications of n-half digit numbers. So if this number had 1,000,000 digits and this number had 1,000,000 digits, then each of these smaller numbers has only 500,000 of digits. What happens if we now, in a stupid way, just make 4 recursive calls? So this is a sequence, these are two shortest sequences of digits. We make a recursive call that will tell us what's the result of a multiplication. This doesn't help us at all, and we can see this either by doing master theorem and actually deriving the time complexity from the recurrence, that the time needed to multiply two n-digit integers is linear time in n plus 4 recursive calls on problems of a half the size. But we can also see it much more obviously. What happens at the very end when you will split? So we are splitting the number into smaller and smaller chunks of digits, and each smaller chunk of digit is combined with each smaller chunk of digits from the other number. And when you get at the very end, you are left with just one digit from one number, one digit from the other number, and then you multiply them. So in the leaves of this recursion tree, you are still doing each and every one of those multiplications, one digit from that and one digit from this, so it is still quadratic, it doesn't help at all. But now comes the main trick of the Karatsuba algorithm, and the main trick is as follows. So instead of computing this separately and this separately, what you can do is you can spend linear time to compute A2, which is A0 plus A1, and compute B2, which is B0 plus B1, and then you make only 3 recursive calls. The first recursive call is this, the second recursive call is this, and the third recursive call is A2 times B2. So you will get the value A0 B0 plus A0 B1 plus A1 B0 plus A1 B1 as the result of this recursive call. And when you know the results of these 3 recursive calls, you can take this one and this one, subtract them from the third one, and what you are left with is exactly what you wanted here. So instead of making 4 recursive calls, we are making just 3 recursive calls. This is the moment when we give up on trying to guesstimate from the top of our head, and we actually look up master theorem, plug in the values, and we learn that the time complexity is no longer n squared, it is n to a slightly smaller power, something like n to the 1.7 or something along those lines maybe. No, I think this is close to the square root actually. It's slightly bigger than 1.5, I think is the exponent in this particular case. The 1.7 ish is for Strassen and for matrices, and doing the similar thing there. So this is something that reduces the time complexity from n squared to almost, but not exactly, but for practical purposes, to n times square root of n, roughly. That's, you can use this as a rough estimate. So you can multiply two n-digit numbers faster than quadratic time. And there are actually even better approaches, and these are based on the fast Fourier transform or on some discrete versions of it, the number theoretical transform or whatever you like. It's possible to do this multiplication if, like, again, there are different ways of looking at the actual time complexity, but as long as you are working with numbers that fit into your like machine world and you don't care about the possible imprecision or whatever, then like the number of mathematical operations is roughly n times log n if you are using any flavor of these Fourier transformation type multiplication. So it is possible to do this multiplication even faster than using this trick, but this is actually something that may still be useful in competitions, both in situations when the values are so big that you would run into precision problems with Fourier transform. This one is completely discrete and everything is finite, so it doesn't run into those issues. And also in situations where you can afford it, because it is much easier to implement, and also for like some range of values, this can even have a better constant still. So there is some range of intermediate range of values where this is the actually fastest way of multiplying things. Okay, so but yeah, I will leave the details of doing those better multiplications to you. And now I will focus more on talking about some fun applications of this. So, first of all, most of the techniques we came up with for multiplication of big integers aren't actually multiplying big integers. What we are doing is we are multiplying polynomials. So instead, if you have a big integer a, you can look at the sequence of digits, and it is very practical to say that as you have the digits a0, a1, and so on, that actually digit with the index I is representing the i's least significant digit. So it's nice when you can say that the integer a is the sum over of I of ai times 10 to the power of I. So if you were to store the digits in an array, it is practical to start with the least significant digit at the beginning. And now the main trick is that instead of doing this in base 10 or base 2 or whatever, what we are actually doing is we can just be doing this generally. So we still have the very same array we had in the beginning. And for the very same array, the numbers we have there, we can view as coefficients of a polynomial. So this is a0 times x to the 0, so this is just the constant term of the polynomial, a1 times x, a2 times x squared, and so on. Now, if you have this polynomial, and you substitute a constant for the value of x, you will get the value of the polynomial in this particular point. So in particular, if you start with the digits of a large number, and you take this polynomial, and then you evaluate the polynomial for x equals 10, if those were the base 10 digits, then the final value you would get is the value of that number. And what you can do now is you can take two such polynomials, a of x times b of x, and multiply those together. And you will get a new polynomial, and the statement will still be the same. So if you put x equals 10 here, you will get the value of the first number. If you put the x 10 there, you get the value of the second number. So it must be the case that when you compute this, and you get the product of those polynomials, which is new polynomial of like twice the degree. If you plug in 10 into the new polynomial and you evaluate it, you must get the value of the product. So if you can multiply polynomials, you can directly multiply integers as well. And it turns out to be the case that all of the techniques we are using to multiply efficiently are actually usable for polynomials. So this is how they were developed, so we can multiply polynomials, and then the fact that we can use them to multiply integers quickly is just a consequence, because it's a simpler version of the same problem, essentially. Yeah, you can, yes, for the technical details of how this works, it's good if you are familiar with having bigger digits. So, yeah, you can have a representation. So the final polynomial can look as follows, for example. So 3 12, and 4. Yeah. So if you would have 3, 7, and 4 in an array, and you would go back from this being a polynomial to this being a number in base 10. So this is an array that represents the number 473. If you multiply the polynomials, then you multiply each term with each term, and then you sum it up for each of the powers of x. Then you can get individual coefficients of the final polynomial that are bigger than 9. So these are not valid digits in base 10, but it's still the same number. So it's still 3 times 1 plus 12 times 10 plus 4 times 100. So in this case, this would be 523. Yeah, so this is what you got when you multiply the two polynomials together, and when you are evaluating it for x equal 10, you are just propagating these bigger values along the array. Okay, so now we have multiplication of polynomials. So what do we get? We have the polynomial a. This is the sequence of its terms. And we have the polynomial b. This is the sequence of its terms. We multiply them together. And the outcome is in the new polynomial c. Then we'll have, so the degree of c is the sum of the degrees of a and b. This is the largest non-zero term in each of them. Then so this is x to the a, this is x to the b, and this will be x to the a plus b, the largest non-zero term in the product. And what are these terms? So the units term is simply a0 times b0. Let's say for simplicity that both of these have length n, then this has length 2n minus 1, and this term, the final one, is symmetrically a n minus 1 times b n minus 1. So the largest coefficient here multiplied by the one here is the last one. This value here will be a0 times b1 plus a1 times b0, and the value in the middle would be a sum of n terms, so this will be a0 times b n minus 1 plus a1 times b n minus 2 plus and so on plus a n minus 1 times b0. So if you use an efficient algorithm to go from this vector of coefficients and this vector of coefficients to the vector of coefficients of the product, the meaning, the values you will get here is this. So you can imagine this as if so in any of these terms, it is a sum of these smaller products, and as one of the coefficients increases, the other one decreases appropriately. So it is as if the two sequences were going against each other, and when they meet, then they get combined like this. And this is essentially what we mean when we say that we did that convolution of those two sequences, is that we computed the values of these things. And again, we are using a smart algorithm that goes from this and this directly to this without individually having to compute each of these. So we don't know what the individual terms are, we just know the value of the final sum. This is what we get in this particular cell of the output. And when we are doing such a convolution, we can do it like this in a vector, but we can also do a cyclic version. So if we split the array here and then move this piece like this, so we equivalently you can view it like adding this value to this one, and then this value to this one, and then that value to that one, and so on. In other words, if we are using the indices into array C in a cyclic fashion, what do you get? So this one would be A0, B0, and this cell we are adding here will then now be A1 times B n minus 1, A2 times B n minus 2, and so on. And if we do it like this in a cyclic way, and then in each and every one of these cells, we will get a sum of exactly n of these small terms, and this is always going cyclic in one. So as we are going with the indices from here, then in the other sequence, we are going with the indices in the opposite direction and always starting at a different point. So in one of these cells of the output, if we do it cyclically like this, we will get a linear combination. So if we are working with these as vectors, these are essentially scalar products. So this particular cell here in the middle is the scalar product of this vector and this vector. And each of the other cells will now be the same thing, but the vector b will be rotated by one step. So we get a scalar product of this and that, a scalar product of this and that, this and that, and so on. All of these cyclic rotations will be the values, the n values we will get in the cyclic array like this. So this is a cyclic convolution. We can also do the same thing, but if you don't like the fact that the b is reversed, so that we are going along A in one direction and along B in the opposite direction, and you want to do the opposite thing, it is very easy. The only thing you have to do, before you start doing this computation, reverse the B. If you reverse the B and then you multiply the two vectors, you get the convolutions where all of the sequences are going in the right direction. So by computing the product of A and B reversed, you will get a new array, again of length n, and the values in this array are A scalar product with B, so A0, B0 plus A1, B1 plus A2, B2, and so on. A scalar product with B starting from 1 plus B all the way towards 1 only, and then rotated by 2, rotated by 3, and so on. So you get scalar product of the original array A and each cyclic rotation of array B. So this is what you can do with the cyclic convolutions. And now, yes.
Can you repeat the rotation part? Please?
Yes. Yeah. So I'll go one step farther back and say those things one more time. So we had an array A with indices from 0 to n minus 1. We had an array B with indices from 0 to n minus 1. If we take these two arrays as the coefficients of two polynomials, we can now use the FFT or whatever similar algorithm for polynomial multiplication to get the actual coefficients of the polynomial C, that is the multiplication of A and B. So this is the array of coefficients, and these things that are written here down are the meaning of those coefficients. So if you were to compute it by hand, this is how you would compute the individual values. And we like the fact that this particular value is the scalar product of A, A0, A1, A2, and so on, and the B reversed, B0, B1, B2, all the way to Bn minus 1. And we can use this array to obtain not just this particular scalar product, but the scalar product of A and the reverse of B, and rotated by an arbitrary number of steps. And this is because each of the remaining scalar products has been split into two. Part of it is here. This is the only term where the sum of the indices is 0. And these are all the terms where the sum of the indices is n. These are the terms where the sum of the indices is 1, and also n plus 1. And this is just going around the circle once. So if we, instead of viewing the array C like this, so it's a string, we can view it as being on a circle like this, from 0 to n minus 1. And when we get to n plus 1, and so on, this will be contributing to the same cell. And you will see that this is exactly going once across A. So each of the terms in A will appear in exactly one of these terms, and also each term of B will appear in exactly one of those terms. So you could say that you are starting from A0 and B0, and then you have A1 and B minus 1, A2 and B minus 2, A3 and B minus 3. If all of the indices are modulo n, then n minus 1 is the same as minus 1. So this is still doing the same thing. So if we take C and wrap it on a circle like this, then you will get all of the possible scalar products of A and rotated reversed B. And if you want scalar products of A and rotated B that isn't reversed, you can get rid of the reverse by doing the reverse manually at the beginning. So instead of taking the array of coefficients A and the array B and then doing the multiplication, you take A, you reverse the array B, and only then you do the multiplication. And then you will get the opposite order of the array you used, which is the original order you actually wanted. And now, why is this useful? One of the main things you can do with this, and this is very useful when doing data science and analyzing stuff like time series. So suppose you have data on some variable, how it is changing over time, and you want to find out about the periodicity of this data, but there is all kinds of noise in the data, and some like weaker but still present periodic factors do not have to be too visible to a naked eye even if you plot it. But you can extract actual numerical data on periodicity by thinking about this in this way. So suppose you have your actual data, and then you take your data shifted by some number of steps, and then you would do the scalar product of the overlap. What happens? So if you have some kind of periodicity in the data and bigger values and smaller values appear in some periodic fashion, and this particular shift happens to hit a multiple of that period, what will happen is that generally bigger values in the shifted version will get paired up with bigger values with the original version, and smaller ones will get paired with smaller ones. So in general, you will get a bigger value of the actual scalar product. So what you would like to evaluate is essentially go over all of the possible shifts, and for each of them calculate the scalar product of the overlap and normalize it to get the average for one cell of it, and then the values of the shift where you get the largest outputs correspond to like the most visible periods in your data. And you can do this in quadratic time, obviously, by just doing each shift separately and then going in a cycle. But exactly this observation of the convolution actually producing the cyclic shifts and scalar products for us can be used for this observation. So this time we can do it without wrapping the C around. We can do it just by letting the C be a full sequence. And what you can do is you can take the polynomial that represents A and multiply it by the polynomial that represents A reversed, so that you are not doing the convolution of A and A backwards, but you are doing the convolution of essentially two equally orientated copies of A. And once you compute this, then the values of this polynomial correspond exactly to what you get the scalar products at these overlaps. You can divide each of them by the length of it and look at it, and you get information about the time series, about the periods in it. So this is called an autocorrelation, and this is an important tool that can be, in which this can be used. But we can do all kinds of crazier stuff with it as well. So we can also do substring search and all kinds of variations of that. So for example, imagine that we have a sequence, and I will use the character CGAT because it's very popular to talk about DNA. It's actually, in terms of being a metaphor for this, it's not actually that useful, because on DNA usually there are multiple types of errors, and in particular there are not just errors that when one of the letters changes, which will be relevant in a moment, but there are also errors that some letters may disappear or new letters can be inserted, and those are the type of errors this particular technique cannot deal with. So, but for now, let's do exact search. So we have a very big string of over some alphabet, and for simplicity, assume the alphabet is of a small size, and we have another string that can also be very long. And now humor me, because I know that you know how to do substring search efficiently in n+n time in 10 different ways. But I will show you an 11th one, which will be interesting in a moment. So how can we say where this shorter string appears in the longer one? One straightforward way of doing this is focusing on one character at a time. So instead of just directly comparing the strings, let's think about it in this way. I'm not saying this will be completely efficient or like the method you are supposed to be using for this particular problem, but it's some technique I want to demonstrate. So imagine that for the original string, you will write down ones at the positions where the string has a C, and you will write down zeros everywhere else. And for the string you are trying to find, you'll also write down ones at the position where there are C's, and zeros everywhere else. So now you have two strings, two vectors of zeros and ones. What happens when you do a convolution? When you do a convolution of these two sequences, and in particular you reverse this one again before doing the multiplication so that you are going along both sequences in the same direction, what happens now is that for each possible cyclic shift of the shorter sequence against the longer sequence, we have evaluated this particular scalar product. And what it is telling us, if we are matching up 0 with the 1, it means that there was a C here, but there wasn't a C there. If we have two zeros, it means there are two different characters. But whenever we see a 1 matched up with a 1, it means that a C in the shorter string was matched up with a C in the longer string. So for each of these possible shifts, we will get one value in the final out. So when we multiply this by the reversal of this, we get a new vector. And the values of the new vector is for each possible cyclic shift, starting with this one with just a single overlap, and then with that one with just a single overlap. For each of the possible cyclic shifts, we get the sum of these individual products. And these products are zeros if there is a mismatch or two different characters. And it is 1 when we matched up the C to a C. So the final value we get at this position is the number of C's in the shorter string that were matching for this particular shift with the C's in the longer string. So what happens now if we do the same thing 3 more times for the G's, for the A's, and for the T's, and we add it up. So for each of the offsets, we now get the number of matching characters. So in this sense, when the only allowed edit are changes of a letter, we have now found all of the most promising matches of the shortest string in the longest string. So not just exact string matching, these are the exact places where it appears, but we got all the information if there is no exact match. What are the places where the match is the closest, where most of the letters match? And of course, you don't have to do this 256 times in a row if you have an alphabet of size 256, so normal ASCII characters. You can instead view both the original sequence as a sequence of bits, individual bits of letters. You can view the other thing as another sequence of bits, and then you do it just twice. You do it once for zeros in the sequence, comparing to zeros in that one, and once in this sequence, and once in that one. Of course, you will get some useless information because some of the shifts will correspond to shifts by half a letter or 7/8 of a letter, but you can only look at every 8th step in the output array and get the outputs. So you can do approximate matching like this using convolutions. That's already fun, but it's twice the fun if you move to 2 dimensions. And you can use these convolutions to do interesting stuff also on images. So let's start with a very simple example, and this is blur. So how does blur look like? You open your image in GIMP or in Photoshop or whatever graphics editor you prefer, and now you select the filter and you say apply blur. And it will ask you for a radius of the blur, and then it will produce a new image that is the original image but kind of blurred, so everything is like spread out and averaged out. So what is going on there? So the new value of a pixel is computed by looking at the surroundings of the pixel within some radius, and then computing a weighted average of all of the pixels we see in this area. So depending on the type of a blur, you can see like Gaussian blur and some other types. This name, the type of the blur, is telling you how the distribution of weights is computed. But essentially, you have the distribution of weights, and then for each pixel, you would apply this by like summing up all of those surrounding colors, each with some coefficient that is between 0 and 1. The sum of those coefficients is 1, and in the end, you will get the new color for the new pixel, which is kind of an average of the surroundings of this pixel. And again, this is something that we can compute using brute force as long as the radius of the blur is small. If we get to a big radius of a blur, then this will be quadratic in the size of an image, because we essentially, for each pixel of the output, we need to traverse essentially all of the input image and sum up everything with some specific weights. So, is there a smarter, faster way how to do this type of a blur? And the answer is yes. So, instead of the big picture being a two-dimensional array, imagine it as follows. So, this will be row 1, row 2, and so on, all the way up down to row n. Or let's, yeah, it doesn't really matter. And now you can imagine, this is essentially how it also can directly be stored in memory. But instead of this being a two-dimensional array, this is a block of memory where somewhere there is the first row, and now it will be practical to leave some kind of gaps between the rows. So let's say that slightly later there will be a second row, there will be again a gap filled with zeros, a third row, and so on. And now if you have a pattern like this, so this is something you can compute once. This is the, you were given the radius of the blur, so you know the size of the smaller matrix, that is the one you are trying to apply onto the bigger image. And you can also just use the formula for your particular blur type to calculate all of these actual coefficients. And now this particular matrix can also be represented in memory in exactly the same fashion. So what we will do is we can imagine it in memory. And suppose we can shift it to the upper left corner. So this is the canonical location number 1 for this particular place. And it will look like this. So this is the blur block 1, and this will be the blur block 2, and this will be the blur block 3. And it will end sooner than the image ended, because in this figure it has fewer rows, but we are keeping the same offsets that we are using for the original one. And now, if we were to compute the scalar product of this vector of some information and interleaved with zeros, and this information, we are doing exactly the calculation of what happens if the matrix is applied at this particular location. And now if we shift this vector in memory, then we are just shifting this matrix along the image. So the other shifts of this vector, in comparison to this vector, the other elements of the convolution computed between those two sequences will be the different placements of this particular blur matrix. And each and every cell of the convolution output will get you the particular weighted average. There is one more trick that needs to be done, that if we are computing the blurred version of this pixel, this is actually the matrix shifted like this. So part of it is outside of the image, and we are actually doing only the sum of these weights, and therefore you have to normalize it because some of the pixels are remained unused. So this is something that still needs to be fixed. You need to be able to tell what part of the matrix is actually within your image. This is easily fixable by doing one more convolution, and instead of having the actual colors here, you will have ones here everywhere, so everything is full, and then the convolution will tell you how much of those ones you actually hit. So the sum, the value of the second convolution will be the part of the blur matrix that is actually inside the image. So this is how you can do blur, and this is also how you can do approximate sub-image search, right? Because you can do the exact same thing we are doing here. Instead of recomputing the coefficients, so the Instagram matrix with some fractions of 1 as the weights, you can look at each. So the easiest first step is to imagine that both the original matrix and the submatrix they are looking for are just black and white matrices. So you can do this once for the black color, once for the white color, and each time you will do once where the pixel is of the current color and zeros where it is not. And then when you do the convolution of those two sequences, one representing the original image, the other representing the sub-image you are looking for, At each and every place of the convolution, you will get a scalar product of the original image and somehow shifted smaller image, and the scalar product will tell you how many pixels of this particular color are matching. So if you do this twice, once for white, once for black, sum it up, then you will get for each and every position of the small image relative to the big image, how many pixels actually matched. And this is again, it is not in quadratic time, so it is not the size of one image times the size of the other image, but there is just a logarithmic factor, so it's the size of the big image times a logarithm of that size roughly. So this can be much more efficient. So these are a few of my favorite tricks with convolutions that you can do crazy stuff that doesn't really seem at the first glance to be related, but it is. All right. Let me now check the clock and see how much time we have left. Almost none. So I will conclude my lecture with a few very quick instructions regarding today's contest. So as you may have noticed from the very short message in the contest system, today we are going to try doing a team contest for the first time, and the plan is for the remaining two contests to be team contests as well. And we will be trying for, again, ICPC rules as much as we can. So you should be using one computer per team to do the actual implementation. As we don't have facilities for like printing problem statements for everybody, feel free to use your other computers, like essentially read only. So you can read your problem statements on your on the other computers, and you can also use them for printing. So whatever you submitted, you can open, look at it, and try reading your code when you are not using the official coding computer for it. But other than that, yeah, you should use only one computer to implement the solutions. Yeah, feel free to register a new account for your team if you want to, or just reuse the account of one of the team members. I don't really care, just it's for you that you know that you can identify yourself in the scoreboard afterwards. And yeah, again, I will leave the information there on how to contact me if you would have any questions during the contest, and I will try either before the contest or very quickly after it starts to post the time limits for today. There is at least one problem where it is relevant, but that one already says about itself that its time limit is slightly bigger than you would expect. Okay, so thank you for your attention and good luck in the afternoon.